Okay, so let's start the course. Okay, so as Natalia said, I'm José Vicente Abellán-Nebot. It's just here. I'm associate professor at the University Jaume I, Universitat Jaume I of Castellón. I'm going to teach you this course that is going to be around 4 hours. The idea was to split the session in 1 hour as a theoretical part and 3 hours of using SolidWorks in the injection molding tool. Um, okay, that's the idea in the part that it's the practical part. The idea was to stay 1 hour and 1 hour and a half that I will use the tool and I will show you how to do the simulations, and the rest maybe 1 hour or something like that, 1 hour and a half. The idea is that there are some exercises, so you can do the exercises by yourself, and you can ask me if you have some doubts. Because this type of courses, I think that the best is just working by yourself. Because if not, you're going to see my explanations, but you don't really grab the ideas. So that's the purpose of the course. Okay, so let's start. As I said, it's basic concept of injection molding. So maybe some of you already know most of what I'm going to teach you here. But anyway, I think that it could be nice for a very general audience. So let's start. So I'm going to explain you the basic concepts in 3 ways. I mean, in 3 parts: the fundamentals, analysis of injection molding, and common defects in injection molding parts. Okay, so for fundamentals, I guess that all of you know what's the process of injection molding, but just to remind this type of processes, you see that it's a very common process for thermoplastics. Remember that thermoplastics, we are talking about ABAs, that is one of the most important plastics that are used in injection molding. I don't know, polycarbonate, polyethylene, or whatever. Okay, so there are many thermoplastics that are used in injection molding. Is one of the most important manufacturing processes in plastics. And the equipment that we need to use for injection molding is this type of equipment. So you can see that all this is a injection machine. This injection machine has 2 parts. We have a injection unit. Here is where we are going to produce the injection. We will melt the thermoplastics and we will inject the thermoplastics in a mold that is here. This is the mold. And we have another important part, important unit, that it's the clamping unit. Okay, so this clamping unit, it's the unit that it's quite big because we need to really keep the mold fixed during the injection molding. And the injection molding, the pressures are really high. The pressure, usual pressure that we use here, it's maybe I don't know, 50, 100 megapascals. So at the end, we need to have a very strong clamping unit to resist to avoid that the mold is going to be open. So this is the 2 basic units. So how it works, it's clear. We have some material that we put here in the feed hopper. The screw moves with this motor, so all the plastic is going to be hit here with these heaters, and during this process the thermoplastic is melt, and when it's here there is a injection. So we inject all the material in this cavity in the mold. So after cooling we open the mold and the part goes out of the mold. Okay, so this process is very important in industry, but one of the important issues that we have here is that we need a high investment. So usually to produce a mold, the mold is quite expensive. So maybe we are talking about, I don't know, maybe 6,000 euros. But if you want to have a very complex mold for complicated parts, maybe you move to 50,000 euros, and so on. Depends of the complexity. But imagine that you want to produce a few parts. So you want to produce a few parts. Obviously, injection molding is a very expensive process. So that's where we find rapid tooling and so on, where we can produce tools that are molds very with a very low in a very low quantity, so you can produce parts, but in low quantity because these molds, the life of these molds are very small. But this is another topic, okay, about the rapid tooling. Just remember that it's a high investment process. Usually the molds are made of tool steels. We need to manufacture, machine the molds. We need to go to electro discharge machining, polishing, and at the end it's quite expensive to produce that molds. So very good process to produce intrinsic complex forms, a very good tolerance. So in this process, in this equipment, which are the main characteristics when we need to select a equipment, a machine, an injection machine? So the basic characteristics are, this is the first one, the injection capacity. Of course, we need to now, which is the total volume that we can put inside the mold, because maybe we want to inject a very huge part, so we need a very huge equipment where all this volume can be melted and injected. So the first one is the capacity, the injection capacity. In the equipment, you can see the maximum volume that you can inject. So usually the recommendation is to work in 20-80% of this maximum value. So then we have also the maximum injection pressure. It's another important parameter in the equipment. So this is the pressure that we're going to have here when we inject the material. We will see now a data sheet of machine of injection equipment. Another important topic is injection speed. This is the flow rate that we can get in this equipment, and the clamping force. That's very important, because if the pressure that we are or the force that we are having in the mold it's too large, maybe we are going to open the mold during the process. So that means that the process cannot be done. So we need to check the maximum clamping force that we can reach in our equipment. So these are 4 important parameters that could be important to select in when you use injection equipment. So this is an example. These are different different injection machines. This is a model. These are from a Chinese manufacturer. Okay, so this is in the website. So you can see there are different models, and here you have all these specifications. So here we can see the clamping force. That is one of the key characteristics that I said before. So for instance, in this equipment, we have 68 tons. This is the maximum clamping force. So when we use SolidWorks simulation, if we see that we need higher clamping force, we can't inject this part. So in the injection pressure here, it's another important parameter. You see here, these are in units kilogram centimeter square. So this is mainly if we remove one digit, this is bars, sorry, megapascal. So this is around this 68 megapascal. You see that this is around 157 megapascal. So the units that we will see in SolidWorks are megapascal. So this is what the maximum injection pressure that we can have with this machine. And the volume, it's here, or the weight. You can see the weight with polyester, or the volume that we can inject. So we can inject a maximum, for instance, here in this equipment, depending on the screw diameter, depending on the type of the screw that we have, we can inject all these different types of volumes. Okay, so this is just to see that it's important to realize that there are some conditions and requirements in the injection machines that we need to consider during simulation. So other basics of injection molding, we have here some characteristics about let's say the design of the mold. So we start first with the selection of the nozzle and the sprue. You see, this is a typical part that has been injected. So this is the injection, and the material goes from this side, and then we fill all these cavities. So here, this is the sprue. So this part is called the sprue, and the sprue is obtained with a part in the mold that is something like that. So here is like if we have this part here. So because this is the final injected part, and this is the the insert that we have in the mold to create this sprue. Okay, so this is the sprue, and this is the nozzle that we have in the machine. This is the nozzle. Okay, this is the nozzle. So you see here that it's important that in our design, in our mold, the sprue should be bigger. The sprue, the entrance of the sprue should be bigger than the end of the nozzle and have a good connection. Okay, so in this case, this is not a good. This both are good designs. This is not a good design because when we inject from the machine, part of the injection could be out of the mold. Okay, so these are some ideas about design that should be important to consider to make more efficient and without problems the injection process. So remember also that the sprue should be tapered. So we have to design a sprue that it's something like that. Okay, so it's from the small diameter, from a bigger diameter. We have here a taper of 1 degree to 3 degree. That is to facilitate the extraction of the part. So other important topics in design of molds, the sprue well. Here is not draw, but here you see that after the sprue, here should be something that is an extension, and this extension is called the sprue well. The sprue well is needed because when we inject, the first part of the front flow has some contamination with the air. So this first part will be kept here, so we have good quality parts thanks to this sprue well. Okay, so sprue well, it's important. This is some characteristics for designing the sprue well. Here you can see that besides the sprue well, we have also in the runner extensions of the runner to act similarly, is to retain all the bad the bad part of the front flow will be kept here. So at the end, the good quality enters in the cavity to fill the cavity. So the sprue well has this design, and something similar happens in the extensions of the runner system. So remember that the runner system, this is the sprue, and all this is the runner system. So this is the runner system. The runner system. Okay, so after the sprue goes the runner system, and then these are the cavities, of course, cavities or the parts. Okay, the parts. So the feeding system, that is also feeding or runner system, that we can say both. Runner system. There are some here. You see that seems that it's circular, but could be with different geometries. So there are some geometries that are preferred, like this one, for efficient to avoid to hide the loss of drop. But usually for making the manufacturing easy, we usually use trapezoidal or even something similar to that. Here we need to machine in both parts of the mold, and maybe it's a little bit more complicated because sometimes it's not exactly in the same line. Could be some draft, okay, some movement. But anyway, all these are preferred. Okay, all the first part. So what more? Here we see some characteristics for designing the feeding or runner system. When this is this could be the nozzle. From the nozzle we move to the sprue, and in the sprue we start with the runner system. This is the runner system. So with the runner system, we may have something like that we have a branching. It means that the front flow is divided in different branches. So this is branching, and when we have that, what we have to do is to reduce the diameter to make to avoid problems about during the front flow. Okay, so the idea is use this equation to divide the runner system. When there is a branching, we use this equation where n is the number of branches, and these are the relation of the diameters, the initial and after the branching. And to design also this diameter, we use this equation, where L is the length of the total length of the runner system, and W is the part weight, Okay, so all these are some information that is from handbooks. Okay, so if you want something more specific, or even the reference from these equations, you can ask me, and I will try to give you the information. Okay, so this is another example of a mold. You see that this is the injection. So we inject from this point in perpendicular to the screen, and then part of the front flow goes here, part of the front flow goes here. Then this is a extension to keep all the bad quality of the first front flow, and then goes here, the front flow goes to the other part. Okay, it's important to have good transitions, round corners to avoid problems. Here we have also another extension to keep all the bad qualities here. And then at the end, we arrive to the parts, to the cavities that are these. In this case, this could be the cavities. Okay, so that's another example. So about gates. So you see gates here. Gates are just the point that enters to the cavity. Okay, so these are the gates. These are the gates. So the gates should have a specific dimensioning. So here we have 3 different types of gates, 1, 2, and 3. So this is called a fan gate. And these are different. This is a gate that it comes from the upper part. So this is the injection, and then goes here to the cavity. Here, this is the injection, and goes here to the cavity. You see that this is from the top, and this is from the bottom. So I don't know exactly the name of these 2 gates. I remember that this is a fan gate. Here in the fan gate, you see that we inject the polymer, and here is like something like a fan. Okay, it's like you open very it's a wide gate, so this is like more uniform, the flow. While here, when you inject, this is not so uniform. So at the beginning here, it's a very the polymer is concentrated in a very small area. So here we open this area. So we may have problems here, issues about jetting, that it's a common error here in injection, jetting, and with this type of gate, we omit the jetting effect. So here we have also some guidelines for dimensioning. So the gate should be 1/4, 1/2 of the channel in section. The gate height should be 50-80% of part thickness, and the length, the length of the gate should be around 1 millimeter. So this is important, so we can remove the part from the runner system. So the gate is the idea is to region to easily remove the part from the runner system. So other topics that are important to have in mind, because later in the simulation we are going to need to decide where to place the gates. So one is the gating location. Okay, so in the gating location, imagine that this is the part. Okay, so if this is the part, where can I add the gate? I'm going to add the gate here. I'm going to get the gate here, here in the middle. So there are many possibilities. So there are here some guidelines to decide where to place the gate. That could be is going to produce better quality parts and reduce the pressure of the injection machine and make more efficient the process. So here you have 3 examples. So the first one is maybe could be the best one for this part, that is to use a fan gate. So you see that the fan gate is that we are injecting here, but the gate is something that it's open. So the front flow is what I'm writing here. So this is the front flow. So we are creating a front flow that is very uniform. So perfect. So if you have front flow that is uniform, that means that you are going to have good parts. So this is a very good quality. So we have a low warpage, good quality parts. So imagine another option, that is that we are going to use many gates from this side. So this rectangular part, that is the cavity, that is the results in this rectangular part, this is the front flow. So we start in the first 0.1 second, something like that. In 0.4 seconds, something like that. Okay, because these are the injections, so we are doing something like that. So at the end, what we have is something like that, and at the end, more or less, is something that is uniform. Okay, so this part is going to be uniform, fine, but at the beginning is not uniform. Here you see, here in this area, we have a overpacking problem. Overpacking means that we have packing too much. All the polymer is getting too close to pack, and at the end, if there is a part in our mold that is too pack, and there are other parts, other regions that are not too pack, at the end that means warpage. That means that the part will have some errors in dimensions. The shrinkage is going to be not good. But anyway, at the end, it's more or less fine. So maybe this is a moderate, but could be an acceptable part. But you see here in the last example, we are injected perpendicular to the screen. Okay? So if we inject perpendicular to the screen, in this case, it's from the side, from this side. So if we inject perpendicular to the screen, this is the front flow. At the beginning, we are injecting all this. Then the mold flow, all in the polymer, it's advancing. So we are now in this place. So at the end, what happened? That at the end, we have a collision of front flows. Okay. So here we will have a weld line, a welding line. That means that this is a bad quality part, welding lines. Okay, so this and also overpacking. Here we will have also overpacking, so that means that the quality of this part is going to be really bad. So you see here 3 designs. Just the part is doesn't change. The part is the same. We are just changing the way of injecting the part. So depending on how you inject the part, you will have very different results. So that's important to have in mind. So then, okay, just to see any question up to this point, just to see if you are there and if somebody can say something, because I don't have any information about the.
We are listening, Jose,
Okay,
but I don't
okay,
know if you have any question or concern. Okay, but we are here.
okay, okay, perfect.
Yes.
Thank you.
Actually, I'm following, so I have no questions. Everything is clear for me.
Okay, thank you. It's the problem is that I don't see chat anything, and imagine that I'm not in the, I'm
No,
offline,
no,
and I'm speaking for nobody, so
I
it's
don't know
fine.
about others if they are having
Okay, it
questions.
is perfect. I will do the same just to see that you are there. Perfect. Okay, so as I said, this is important, the gate location. So here we have another example. We will see this in the simulator. It's important to try to place the gates to balance the front flow length. So if we inject from this point, you will see that here this is the front flow, and at the end we are here. So this part of the cavity has been filled, so it's fine, but here it still needs some time for filling. So if you see, while the polymer is from running to this side, here it's already in the wall of the mold. So here we have overpacking. That means that we have a two pack in comparison with the other side of the part. So at the end, the problem, this means that we will have some issues of warpage. Warpage is that the part will have some errors in dimensions. So Another option is, okay, I'm going to put 2 gates. If I put 2 gates, in this case, I have a balanced front flow because here we are starting to inject. So the polymer runs, and at the end, we reach this part, we reach this part, we reach this part, and from the same, from this other point, we reach this part. So at the end, what we have is a balanced flow. So this at the first side could be better option than the other one. The problem here is that due to this front flow, we have a collision of front flow. So that means a welding line. And a welding line, that means that here we have a defect that you can visually see this defect. And also this zone could break easily. So depending on the part, maybe this is not a good option. Okay, so that's something
Okay,
that,
I have a question here.
yes,
So the software will help us to design this type of things, or
yes.
we need to have the experience.
Okay, in the software will give you the information about the welding line, for instance. So you will simulate this option and you will simulate this option. And the software will show you that here we have this problem, and even warpage that we can see in the software. You will see that maybe here you have more warpage, but no weld lines, and here you have less warpage, but
Okay,
welding lines. So this
so
is
it
something that you have to decide. Yes.
okay, so it is also depends on the experience as well.
Exactly. Yes, yes, yes. The software is not going to say that this is the best design. No. You can just, okay, because this is an analysis software. I don't know if there are some the other way, no, like that you do the like the synthesis, no, and you can say, okay, I have this part. Tell me which is the best one. No, the software can give you, and we will see that the best place of the gate, but the software is going to give you the best place of the gate according to this, to balance the front flow. So if you put the this option in the software, if you put 2 points, will give this solution. If you put 3 points, will give this one, maybe this one, and this one. I don't know. But the idea is that the program will give you the best place to balance the front flow. This is something that the program will give you, but only that. The rest is just experience. Okay, as you said.
Okay, thanks.
Yes. Okay, so this is something that maybe is not so not important than that. This is more related to designers, okay, for the designers. But imagine that you have that part and you want to put only one gate in and create that the material will reach at the same time everything. So it's a balanced front flow. So you can do it if you modify the thickness of the part. So if you modify the thickness of the part, imagine that this part, this front flow, this section is going to be a small section. Let's see that the thickness is going to be low. And here in this part, that the path is longer, we are going to increase the thickness. So that means that when you inject here that the thickness is very small will be slower, and here that the thickness will be higher will be faster. So at the end, you're going to reach all the parts, all the walls at the same time. So you have less overpacking problems. Overpacking is reduced. Okay, but the problem is that you have to change the thickness, and also remember that changing thickness is not also a good strategy in plastic design. Okay, because usually if you see any handbook, the key the key guideline is uniform thickness. So every handbook say that always try to make thickness uniform to avoid defects like sink marks and so on. But in some cases, if you have problems of overpacking and warpage, maybe could be a good solution. Okay, but in general, always try to design parts with uniform thickness. That's a important characteristic. So other characteristics here about gating. So we can gate in large parts. You see that in large parts it's better to gate in one side. So this is the front flow. and you will have better parts that if you gate in from one side, because here we have our packing and here there is no air packing. So at the end there is a warpage. Okay, you see there is a bending. In a cylindrical parts, always try to gate in the middle, so it's better than not gating in one side. That will be warpage problems. And also if you have designs like this one, this is like a grid. So if you inject from this point, you see that this is the front flow, and at the end when it reaches this part, you see goes here and the front flow goes here and goes here. So at the end you're going to have a welding line. And remember that a welding line, it's a bad quality. Let's say that it's a line with a bad quality and bad mechanical properties. So if you have a welding line just here in a very slender part region, so you can have issues about being broken. So it's better maybe to redesign the part. So in this way here you will have, this is the front flow, so the front flow will be here and the welding line is just at the end, not in the grid, just at the end of the grid. So this could be a better design, or even gating here. So here there is no welding lines and the welding line will be here. And this welding line, well, it's in the middle and maybe it's not so critical. Okay, so there are these are concepts of design that the simulator will give you some advice because you will see the welding lines in the program. So other strategies: place gates in thick zones, avoid gates at zones mechanically critical. This is the example like before. And here it's important, we will see this in the simulator. If you see that you have a part, for instance, and you put one point, just one gate, and you inject, and for any reason you don't finish the part, that means that the pressure is too high for you and you don't have enough height in your pressure in your machine to finish. The good way to avoid this is to add 2 points. So if you add more gates, you will reduce the pressure. So more gates means that the pressure will be reduced, the pressure that you need for filling the part. So if you have a machine that you have just 100 megapascals and you put one gate and you see that it's not enough for filling the part, you can try adding 2 gates. So you try with 2 gates, probably you are going to be able to fill this part, but not with 1 gate. So we will see an example where you need to add more gates to be able to fill the part, because the part is difficult to fill. So you add more gates. The problem, if you add more gates, remember that we will have welding lines. So if there is no welding line, if there is just 1 gate, the welding lines will be difficult to be created because you need different front flows. But if you have different gates, for sure that you will have more welding lines. So the problem here is that you reduce the pressure, but you will increase the welding lines. That this is something that we don't want, but it's something that happens. Okay, so this is important to consider here. So other characteristics about bending. That's important because when we inject the polymer in a mold, the plastic will push the air that it's in the mold, because when we close the mold, there is air in the cavity. So the polymer is pushing the air, and we need to escape that air. So we need to create small holes. Imagine that this is the cavity. So we need to create a small holes here, or here. We can see better here. So this is the cavity or the part. Let's see the part. And we inject all this. And we need to create here a small hole that is called a venting. So when we inject here, this is the feed runner. So we are injecting the plastic from this side, we inject all this, and this is the last part of the mold that will be filled. So we need to create a small venting, a small hole to make possible to escape the air. Okay, so that's the idea. So if we don't create a venting, all the air will be packed at the end of the injection, and we can have problems of burns or something like that. So we can have a burning issue. Okay, because we need to let the air escape. So some examples of venting design is this one. So we can create a small holes with this dimension. If you create a big hole, the problem is that the polymer will escape, and you want to make the air escape, not the polymer. Okay, so that's the idea of very small holes to make possible to remove the air. So here, this is important that the SolidWorks will give you where to place the venting, okay? Because you will see where the air is concentrated. So if you see where there is an air trap, you will see in the program air traps. So if you see an air trap, that means that you have to place a venting there, because if not, you will have a burning issue. Okay, that's the idea. And also we can see we need to design the cooling system. We are not going to see the cooling system in this course, but it's important to know that in this type of program, SolidWorks or others, you can simulate the cooling part. Okay, so you can indicate which is the temperature at the entrance, which is the temperature. You will see the temperature at the end of the cooling system. You will see the progression of the cooling and so on. So all this could be designed in these programs, but we are going to see only filling and packing. Okay, so remember that there are, we will see later, but there are 3 stages: filling, packing, and cooling in injection. So this is also an important part. This is balance runners. So you can see that if I inject it from this point, the good way to design a mold when we have different cavities is that the path that the mold, the front flow needs to follow for reaching the cavity should be the same in all cavities. So this is a balance design, okay? A balance runner design. Here, this is not balanced, because if we inject from this point, and this is the mold, the front flow, you will see that we will reach here first than this one that will be filled at the end. So this will have overpacking and this have not overpacking. So to avoid this, or one option, you redesign the mold with this scheme, or you design different diameters of this runner system. So the idea is something similar that we see before. This has a thickness that is very small, so the front flow will be very slow. And here we have a thickness that is higher, so there is no resistance to the flow. So here the flow goes very fast. So if you redesign this, you will be able to reach the same at the same time this cavity and this cavity. And this is done by the program. SolidWorks can calculate for you these values. Okay, so you put this design and you ask the program, please calculate the balance runners for this runner system. This is the calculation that will give for you the program. Okay, so this is something that is done. You don't need to calculate a balance runner. This is done by for you by the program. Okay, so let's see. Okay, let's finish these 3 parts and we will start with the other part. Okay, so we have different type of molds. We have a 2 plates mold. This is the common, or the basic mold. So you see that this is the nozzle. So here we have the injection. This is the sprue. Okay, this is in Spanish, so you can also learn a little bit of Spanish. This is the sprue. So this is the runner, and this is the cavity. Okay? So this mold is the fixed mold, and this is the movable mold. So these both molds, these both parts are close together. You inject the part, the polymer, and then this mold will move to the left, so we can open the mold and remove the part. Okay, these are the ejectors. The ejectors. So the ejectors will hit the part, so the part will be removed. Okay, so this is a 2-plate mold. There is another type of mold that are 3-plate mold. So you can see that this is the fix. This is the plate here. This is fixed. This is fixed. These both are movable. Okay, exactly the same. We inject here, but you see now is different from this side because we are separating the runner system from the molds where we have the cavity. Okay, that's why we have 3 plates and not 2 plates. So this is easier. This is more expensive, but it's easier to remove the runner system. This is the runner system that is automatically removed in a 3 mold plate. And here you have to remove this. We have to take the part and remove the sprue and the runner system from the part. You have to do it manually. Here in these systems, it's automatically done by the injection molding because you design a 3 plates for making this more efficient. So you don't need to do it manually. You do it um, automatically. Okay, I'm going to see if this works. That it's just a video about.
Jose, just sorry to interrupt.
Yes.
The meeting is going to finish in 10 minutes. You suggest meet, but I didn't realize that we have limit time. So when the call finish, you can go another time in the same link for all the participants. I'm saying, but if you prefer, we can go to Zoom and it's not limit.
Okay, I
As you
can
wish.
also create the meet that is no limit with my account. I mean, it's up to you. It's okay. It's going to be closed automatically, and we have to move to another to repeat the session. Okay, so
Okay.
just
Okay.
write you the if you want, write you the. For me, it's fine. If you prefer Zoom, it's fine. Just
No,
write the.
for me it's okay. It's if you prefer, we can enter in the same link all the time or to another link. For me, it's the same as you prefer.
Okay, but if we use the same link, we will have the same problem in 1 hour. Okay, no, I
Yes,
guess.
yes.
Okay, so it's. I don't know. Maybe I can. If you prefer, I can create the link with Meet, and I can
Okay.
give you the. Maybe it's going to be better because in that way, I have the same interface for me, that not
Perfect.
Zoom. But it's fine. Okay, I finish this
Perfect.
and I move into the to another link. Okay, I will give you the another link. Okay.
Okay, thank you.
Okay, so just to finish this part, you see, are you seeing the? I guess that you are seeing the simulation. You see, this is a 3 mold. You see that it's separated the runner system with the parts. Okay, you will see again another injection. Okay, it's injected cavities, and then you see there are 3 molds. These are the movable, are the first 2. Okay, and then we remove it. Okay, just to see that is a very nice simulation here. Oops, sorry. Okay, so and to finish, there is another variant, another variant that is the hot runner. That means that you keep all the runner. It's always a high temperature, so you don't remove the runner every time. Here you see we are removing the runner, so we need to remelt the runner. So this is not an efficient process. So here in the hot runner, this is always in a high temperature. So we are keeping the runner polymer here, and we are injecting in every time the runner system to the cavity. So this is the final injection. So we keep all the runner in the mold and for the next injection. So that's more efficient, but obviously it's more expensive, this type of molds. Okay, so with this, it's the fundamental. So let's see about to change the link. Okay. Yes, 4 minutes. Okay, let me try to create a new one, and I will stop here. So let's see. Okay, so this is a new link for Meet. You see in the chat, you can see if it's working, and we can move to the other Meet.
Okay.
Okay, I think it's we are all here. Okay, so I'm going to close the other session, okay, and we can stay in this session. Okay, nobody is missing. Okay, so now I have to
I think
record, I guess.
I think around 3 people missing because we
Yes.
were 11, no?
Okay, let's see. Now one more. I have to admit them, but I think it's no problem. Yes, we will wait a little bit. Okay, now let's see. I was going to start with the injection molding analysis. The problem is that I prepare the I prepared the course, and my first idea was to split the theory part, the theoretical part, as Natalia said at the beginning. But later I realized that maybe if we start the injection molding, maybe the theoretical part should be already done. So if you don't have any problem, maybe, and if you don't mind, I will try to be faster. We can finish the theoretical part and then do just everything in SolidWorks. Okay, because I think it's going to be easier for you, because if we start with SolidWorks, the beginning we need to place the gate, so it's fine. We know how to place the gate, but we need to analyze the filling stage, and the filling stage we need to see some basics of simulation. Okay, 11. So I think that we are now fine, Natalia. Okay.
Yes, I think so.
Now I don't know how to record the session. Do you remember that?
I'm recording my computer, not in Meet, so don't worry. If you want, I
Okay.
continue recording.
So you're recording that? Okay, so
Yes.
perfect. Okay, so better. You can do it in Google, but in Meet. Okay, so I'm going to continue. So it's fine for you that I finished the part of the theoretical part, because if not, I think it's going to be a little bit weird for. Wait that I have one more. Okay. Sound okay. Okay, so let's move to the. Oh, wait. Okay. Okay, we'll try to be faster. Okay, so are you seeing the analysis injection molding? Okay, I guess, no? The presentation?
Yes.
Okay, thank you. Thank you. Okay, so analysis of injection molding. Let's see, basically, when we analyze the injection molding process, we have something like that. We have a filling stage. That is, at the beginning, we start injecting. So this is the pressure. Here we have the pressure. This is pressure, okay? This is pressure. And this is time. So at the beginning, we start, and this is something that happens. It's we're increasing the pressure up to we finish the filling. Okay, so now here the pressure is quite high up to this maximum pressure, and the cavity is totally filled. Then we move to the packing stage. So after filling the mold, we need to keep the pressure because it's not solidified. So we need to keep the pressure. So usually we keep the pressure a little bit lower than the end of the filling stage. So usually we keep the pressure up to one point, that is when the gate seals. When the gate seals, that means that we can't keep the packing. We can't keep the pressure because the gate has sealed. So after that, we put zero pressure, but we can't open the mold because the part is still not in a total solidified stage. So we need to wait until it's mostly solidified. So we keep to this point, that is the ejection time. Okay, so this is typically the 3 phases, and this is the cooling phase, the cooling stage. So it's filling, where we are controlling the pressure, then packing, where we are keeping the pressure to compact and to reduce the warpage, and then we finish packing and we just keep the mold closed because we need to wait until the part cools. Okay, so this is the total cycle, and this is from this point to this point. Okay, so this is just for part extraction, opening the mold, release the mold, the part, and so on. So these are the total time in injection, and you see that all this that is quite large is the cooling time. That is this phase, cooling time. So cooling is quite important, and that's why in additive manufacturing it's important something that is called the conformal cooling. This is just a research topic. Conformal cooling. Conformal cooling is to design a very good cooling system to reduce the time. So if you reduce the time, imagine that maybe a normal cooling time is, let's say that it's 50 seconds. If you are able to reduce this, instead of 50 seconds to 40 seconds, it's just 10 seconds. But if you produce 1,000 or not 1,000, 1,000 or even million of parts, because we are in injection molding, that is a process that we inject a lot of parts. At the end, this is a lot of time and this is a lot of money. Okay, so a reduction of just 10 seconds for thousands of parts, it's a lot of money. So conformal cooling is something that has been researched now with additive manufacturing. Okay? With additive manufacturing, we can be able to produce a very, very good cooling system. But for this, we need additive manufacturing. With the conventional machining processes, we can't produce a conformal cooling. Okay, this is just for if somebody is interested in reading something about conformal cooling that is in injection molding. Okay, so let's see. Okay, I'm going to skip this one. The filling pattern, you remember that I told you about that if we inject from this part, we will have overpacking here, and here we have no overpacking. Wait, but I think that we have somebody. Problem is that I have to check if. Okay, was something that. Okay. I thought that was somebody trying to enter the session. Okay, this is the overpacking. So remember that we need to avoid this type of patterns, but this is fine, but here is not fine because it's overpack. So warpage problems, okay, warpage problems. So another problem is race tracking. Race tracking is when we put the gate here, and you see that this is a very thick thickness, and this is a very small thickness. So what happens that when we inject here, all the polymer goes to the easiest way, easiest path. That is the thick area, and doesn't goes up for the thinnest area. So that the problem here is that at the end you will have a very bad filling pattern. So this is something that we need to check in SolidWorks. In SolidWorks, you will put the gate and you will see how the cavity is filled, and you have to identify if you have some issues like that. Exactly the same like before. The problem is not going to tell you this is not a good way to do it. You have to be able to decide to see that, but you will see the pattern, and it's easily, if you have some basics like the one that I'm explaining to you here, you will realize that this is not a good way of filling the part. So here it's another problem that is called excitation, or race tracking is almost similar. If you inject from this part, from this point in this mold, you will see that you are filling, and when the front flow reaches this gap, you will see that it's easier for the front flow to go from this part, to go to this direction. So we'll fill all this, and after filling all this part, we will try to finish this. So we can have a problem that maybe at the end this is frozen and you can't fill this part. So that could happen. So instead of this design, you can design two gates, with a balanced front flow. So you see that here, this is the front flow, this is the front flow. At the end, you are going to fill all this and all this at the same time. You will have a welding line here, but instead of the other case that you have a defect, you have a short shot. Here you can fill all the cavity. Okay, so this is for optimizing the filling time. It's important to know that you see here, this is the time. Okay, I'm going to explain you very fast here, and this is the pressure. So what happens if I try to inject very fast all the polymer for the cavity? If I try to inject very fast, the problem is that I have a very large pressure. My pressure is going to be very large. And what happens if I try to inject all the quantity very slow with too much time? The problem is that I need also very large pressure, because the polymer will frozen. Okay, so it will be frozen. So if the viscosity increases, the pressure to push and fill the cavity will be higher. So the pressure do something like that. So there is a region where it's the best way for injecting. So this is something that the program will give you. The program will give you more or less this value. This value will give you the program. The program will give you this time, this proper time for injecting. But sometimes it's interesting to check and to do it yourself with some simulations. But the program will give you this good region for injecting. So the profile injection, we are not going to see this in the computer session, but it's important to remember that if we inject with a constant speed, imagine that this is my machine and this is the constant speed, and this is my injection, my gate. If I inject with a constant speed, the problem is that at the beginning, this is the front flow, you see, we are going this way, and at the end, when we fill all these corners, this is totally empty, so speeds goes very fast. So here goes very fast and here goes very slowly. So that happens. The problem here is that we will have warpage. We will have problems in the quality of the part. So the to solve this, what you have to do is when the front flow is here, reduce the speed. So we are with a flow rate at the beginning and we finish with another flow rate. So this is a profile. So in industry, if you apply a profile, injection profile, you will obtain better parts. Sometimes if the parts are very complicated or there is no good knowledge in companies, they use a constant profile. But with a constant profile, the quality of the parts cannot be optimized. So it's important to know that you can modify the profile of injection in the machines to get a better patterns, a better filling patterns. You see here the gaps, the separation between the lines means that it's uniform. And here, if the separation is different, that means that the speeds are different. So that's important to consider. So let's see about the basics of filling and packing. Well, filling and packing this is the filling stage, and now the packing stage. So in the packing stage, this is what I told you. The idea is that in filling, we inject, and then when we have filled all the cavity, we move to the packing stage, and then we move to the cooling stage. Okay, so filling, packing, okay, and cooling. So you see here in filling, we control the profile, the flow profile, okay, the flow rate. We control the flow rate. The flow rate, that means the centimeters by second, okay. And here in packing, what we are controlling is the pressure. We control the pressure. So the machines have two stages. One to control the flow rate at the beginning, and second to control the pressure at the end in packing. Okay, so this is something to check. Remember that I told you that we finish packing when the gate is sealed. Gate is sealed. That means that we don't need to, if this is the gate and this is the injection, we don't, when this solidifies, we don't need to keep the pressure of the injection because this is solid. We can't put more material. We can't put pressure here because this is solid. So in that moment, we have to finish the packing. So there are some ways to check when to reach when the gate is sealed. You can use the program to see when the gate has solidified. You can see the temperature of the gate during the time, and you will see something like that. And if you see that this is the solidification, so this is the time that we want. Okay? You can do it in SolidWorks. The second computer session of the course talks about that, how to check when the gate is solidified. And there are other ways to do it. There are people that they do it experimentally, and this is the packing time. So they modify the packing time in the injection machine and weights the part. And when the part weights exactly the same, this constant, then that means that here the gate has solidified. So in this case, I would say that the time of 6 seconds is when the gate has solidified, right? The gate is sealed. Gate seals, okay? So about packing, there are different profiles to pack. So usually the idea of packing at the beginning with a constant and then with a decrease linearly, it's a good profile, but there are different ways, okay, of packing. So just to remember that there are different ways of packing. So finally, defects, some defects that we can see. We can have defects that seam marks in parts. This is a seam mark, you see here. Seam marks is usually when the material has solidified in the walls, and then there is a wrinkage to the center. So this wrinkage to the center makes that the material is pulled, and at the end you have a void, like a mark. So the program will give you information about seam marks. In the program, you have an option to see the seam marks, and you will see the seam marks. And so you can change the design, or you can change the gating or the packing to improve the seam marks. Other typical problem is the short shot. The short shot is when we inject here, and you see that at the end, this is my part. That means that it's missing material. We can't finish the part like that. These examples are example of short shots. So there is no enough pressure to fill the cavity, so there is no enough pressure to finish with a good part. So to avoid the short shot, we can increase the number of gates. This is what I told you before. if you increase the number of gates, you can reduce the pressure that you need to fill the cavity. We can increase the temperature to make less, to reduce the viscosity and make easier to fill, and so on. There are many different options for avoiding a short error. Air traps, remember that this is something that will be given by the program. The program will give us the position of air traps. So here we need to create a venting. In this case, it's not good because the problem is that we had a race tracking problem. So with a race tracking problem, we can't put the air trap a venting. Okay, we have to modify the design of the part to avoid the race tracking problem. But anyway, remember that air traps is important, so we need to check in the simulators where the air will be trapped, and then design a venting in the mold to let the air escape from this part. Welding lines, this is something that we showed before. So there are two types of welding lines. When the welding line is a collision of two fronts, this is a very bad welding line. And when it's something like that this is the front flow and it's a collision, but it's not a frontal collision, it's a lateral collision. This is called a meld line. So a meld line is not so critical than a welding line. Welding line is a very delicate issue, and you have to check if it's something that is a problematic for your part. A meld line is not so important, but remember that it's also something that happens when we have two front flows. Okay. Just two more errors, I think, two more defects. Well, the welding lines is the same like before. Important, where are going to be produced. Here we have a front flow that is divided because we have a hole, and at the end we will create a welding line. So this welding line, you can see it visually, and it's something that can break the part from this side. And here, this is a very bad design. This is a very bad design because we have a gate here, so we are injected from this side. We are gate here, we are injected from this part, and at the end we have a welding line just in the middle of the screw. So this is not a good option. Okay. And the last one is the flash. So the flash is when you have two molds and there is not enough clamping force, for instance. So if you don't have enough clamping force, there is an opening during the injection molding, during the filling stage. So part of the polymer will be out of the molds. So we will create a flash issue. Okay, this is something that happens in injection molding. Okay, so with this, more or less, is the idea of the basics of don't know if you are there. The basics of injection molding. Let's see. So it's more or less the 1 hour. So if you want, we can move to the SolidWorks program, so we can start doing some simulations for the first part, and then in the second part you can work by yourself in some exercises and see if you can more or less do it alone. Okay, so any question or something that you want to say, or we can move to SolidWorks? No question? So we can move to SolidWorks. So what I'm going to do is the first computing session. Okay, so I guess that Natalia has shared with you all these files. So the idea is to start working with this first session. I will explain all this with the program, and then the idea is that you can work with the exercises, with these exercises. So it is something that you can do it by yourself.
Do you have the documents or you need the link another time? in the chat.
No, I have the comment.
Okay.
Okay, so let's start with the SolidWorks. It's fine for you?
I think fine. I don't know about others.
Okay, so okay, so let's see the session. Okay, so we are going to work with a part. The part is part 1. Okay, that is in the files that Natalia has loaded for you. So just open SolidWorks. Um, and then open the part. If you have the version 2020 or 2022, it's fine. I think that this part is modeled by the program 2020, so you will see in the disk like a mark that is saying that it's an old file, so it's not a problem. When you save the file, you will save the file as the actual version of the program, so it's okay. So the first thing to see that all of you have the same, you are in the same page, it's to check that you have this icon. This is Plastic Manager. This is the add-in that SolidWorks uses for the injection analysis. Okay, so to open this, I have others because I'm also teaching computer manufacturing processes, computer-aided manufacturing processes. So this is CAM files. So this is for machining. So I have these 3 that are for machining, but you don't need to have these 3 icons, okay? And these are the icons by default in SolidWorks. So to have the plastic tool, you have to go here to Tools and Add-ins. And Tools and Add-ins, you have here SolidWorks Plastics. Okay, so you have to click on SolidWorks Plastics. And after clicking SolidWorks Plastic, you should be able to see this. If you don't see this, maybe you have to move to this part that is the tabs that you have here, and look for the tab SolidWorks Plastics. And here you have an icon that is a new study. So if you click new study, maybe at this moment you will have the plastics. Okay, so this is the first step. So if you have any problem with this, just say something in with the micro, and we can see what happens.
Okay, if you can just repeat because I was
Okay,
just opening my software.
okay, it's here in tools,
Add-ins.
add-ins. Okay, here it is, add-ins, and here you have SolidWorks Plastics. Okay, so I have others, for example, CAM. This is why I have these 3 tabs, but here I asking you to click here, SolidWorks Plastics. Okay, so with this, you should be able to see this icon. If not, is click here, new study in SolidWorks Plastics in this toolbar. Maybe you have to click here and toolbars. Maybe you need to add the SolidWorks Plastics. I have SolidWorks Plastic, you see here. But the important is just to see plastics, because with this part open, we can click plastics, and then we have the menu for the injection molding process. So this is the menu that you need to see for starting the simulation in SolidWorks. Okay, it's fine.
It's okay.
Okay. Anyway, you have. I will give you like a fast overview of the program with the first computer session 1. And after that, you have your own time for working with the exercises. So maybe at that moment, if you have some problems, we can share the screen and we can see what happened. Okay, so with this, first, we are going to see that we have all of you the same configuration of the part. I don't know if you know that in SolidWorks, you can have different configurations. So here in the third tab, Configuration Manager, you have different configurations here, okay? So actually at this moment, we have one configuration that this call is in Spanish. Sorry, I couldn't change that. Espesor reducido is the last one. So I want you to put the predetermined. So you click here twice. We are in the predetermined state because here are different modifications of the design. Okay, so I want you later to change and see what happens if I change the thickness of the part. What happens if I change the I don't know, this area, and this is thinner than the other part. Okay, so there are different ways of different variation of design. So now I want you to start with the first one, that is predetermined. So remember that is here the third in Configuration Manager, and if you click here, you see 3 possible configurations. So I want you to click at the first one, that is predetermined. That is the same like I think the second one, but anyway, click at the beginning. Okay, so with this we move to the plastic tab. Okay, so here with the plastic tab we can start taking a look to the parameters here. So we start with the type of simulation. I changed the language to English language, but I don't know why part is in Spanish. So here the idea is to change the type of simulation. You see, now you should see something different. Okay, sorry. Maybe you are here in new study. Maybe, are you seeing this menu? I don't think so. Are you seeing this? No.
Yes, we see it, Jose.
No,
Yes,
no,
we see
sorry.
that.
I mean in SolidWorks, in your
Ah,
SolidWorks.
sorry.
It's okay because uh, probably it's okay because you are using the same files like me, but maybe you have to click here in new study, and if you have here new study, then the program asks you the type of study. We have 2 types of study, a solid study and a shell study. If the part is thick, we should use solid. If the part is thin, you should use cell. In 95% of the situation is cell what we have to use, because because in plastics usually it's 3-4 millimeters thickness or something like that, the parts. So we should use cell study, and when if you click cell study, probably then you will see this menu. Okay, so anyway, I'm going to give you the ideas about that, and then we will see any problem that you may have. So the first is the type of simulation here. So the type of simulation, if we click right button on the mouse and click edit, you will see that by default, in my case, I have all the simulation. This is cooling, filling, packing, and workbench. So since the first part of this session is just filling, I'm going to just click filling. Okay, because I'm going to analyze only filling. If you click everything, the simulation will take a lot of time because we are going
Yeah.
to simulate a lot.
Dear doctor,
Yes.
actually, you can just ask if all of participants are following.
What if they are following me? You mean?
Yeah, because I don't know if they have the software ready, or if they opened everything. So if we can check with them.
Yes. I'm saying if all of you are fine and you are following me. I don't know. First, if you have the files for
Because
sure.
you are quite fast. You are doing everything fast. I'm not sure about everything is clear or not.
Okay, but they should say something.
Yes, I know, I know.
So
For me,
okay.
like I missed some points because I am following you in two screens. So I don't know about others as well.
Yes, you're right, because you have to do it with SolidWorks, and then you have
Yeah,
to
we
see
have
to
to
see
follow.
me.
Yes.
So that's complicated. Anyway, I'm just open the program at this moment and just click the plastic add-in. So I don't know if you can tell me something about that. Are you fine, or I can? The problem is that I mean, in your case, do you have the this window, this part of SolidWorks active?
For me, yes, it is clear.
Yes. Okay, because
For
my
me, I don't know about others actually. So
okay.
all of you have the software and everything is right.
You can use the chat if you want and say that you have problems or what or something. Okay, it's
That's
fine.
good.
Okay, I can share my window to see. I cannot open the
Okay, you can you can share the your screen and we will see.
okay.
But this is not this is SolidWorks PCB. This is for creating electronic devices. This is not plastic. So this is not SolidWorks CAD. No, so this is for sure is not going to work. This is another package from SolidWorks. So you need to open SolidWorks, and that's all. No, I don't know if there is another. Let's see.
You should
SolidWorks.
open the main SolidWorks application,
Okay,
not
okay.
SolidWorks for PCB.
Anyone that has some issues? In that case, is the program is you have to open the normal SolidWorks. This is PCB and it's not. This is for devices, electronic devices. And the rest is fine. I guess that if you don't say anything, that you are more or less, at least maybe if you have problems with your equipment, with your machine, at least you can follow my explanations. And when we stay in the exercises, maybe we can see the problems. Okay, because the idea is that maybe half an hour an explanation with the basics, and then you work by yourself. Okay, so if you don't say anything, I'm going to.
Okay, for me, I already opened and I have the add-ins, everything.
Okay. Okay, so let's see. So we stay here, and the first thing is the type of simulation. Okay, so we click with right button and we can click edit. So if we click edit, we can modify the type of simulation. So as I said, it's in Spanish, but I'm going to keep the second one, that is filling, because I'm going to simulate the filling stage. Okay, I'm going to change the simulation. Yes. Okay, so you click yes, and now I'm just filling. Okay, so this is the first thing. Second thing to do is to select the material. So you can go here to unit. There is the injection unit, and with right button we can click different options. So you have the first one, that is, I don't know if in your case, because it's here in Spanish, maybe it's going to be like adjustments or settings or something like that. So the first one is to indicate the temperature of the mold, the temperature of injection, the time of injection, and so on. This is to define the settings. The second one is to edit the type of the material that we are going to inject. Okay, the polymer. And the last one is recently used. Okay, so just to select one from this list. So in our case, I'm going to click the second one, is to edit or to apply a specific polymer. So if you click here, you will see a large quantity of materials that you can use for injection. So you see here, you have different databases. So we have a predetermined database, we have another that is defined by the user, and we have something that is classified by families, classified by vendors, and so on. So actually there is different ways of looking for a material. In our case, we are going to use just one. You can use even whatever you want because this is not going to be important, but just to make the to compare results you want, we are going to use a material that is ABS 6003 from BAS company. Okay, so this is an ABS. So you can go here. In my case, since it's from a specific company, I'm going to click by vendors or manufacturers or something like that that you will have here. So if you click predetermine databases, classify by vendors or manufacturers, you can see all the vendors that we have. So in number 26, we have BASF. So if you click BASF, you will see all the ABS from this company and other materials, but the first one is ABS. So I'm going to select this one, ABS 6003. Okay, this is because I am assuming that I have bought this material from that company, so I'm going to use the characteristics of this specific material from this specific company. Okay, so this is just a screen to select the material. If you have some problems, just click any material because this is not going to be will change the results, of course, but just for following the session, it's enough. And here it's interesting to see that you have many different information of the material, and I like one of them that is called material parameters here. There are conductivity, the curves that are pressure, volume, temperature, and so on, but one that is parameters. If you click parameters of material parameters, you have here interesting information. You have the temperature of the material for injecting 240, the temperature recommended for the mold, the ejection temperature, and so on. So here there are many important characteristics. And I like one here because we are going to use it later for the exercises. This one that in your case should be something that is shear stress, maximum shear stress or something like that. That is 0.29 megapascal. This is the maximum value that is recommended in shear stress. When we use the simulations and we see the results, this is something that is interesting to check that we are not exceeding this value. Okay, so this is in parameters of the material. Okay, but this is just information of the material. So remember here, predetermine database, classified by vendors or manufacturers, and in BASF we select ABS 6003. So we click OK, and then we have already this material selected. Okay, so then next one you see that you will see something that is domains or something like that. This is in case that you want to create the cooling system, we want to create the gating system, and so on. So here this is the gating system, the runner design. Okay, in Spanish is sistema de colada. You will see something that is runner or something like that, channel design or something like that. So here you can design the runner system. We are not going to do that because we are going to simulate this without gating system, just sorry, without runner system, just with a gate. Okay, so we skip this part, and then we have the contour conditions that is related to the injection point and the clamping force. So the injection point, I'm going to put an injection point here. So in this case, I'm going to use this point that you will see here. I have a point here. So I'm going to use the injection in this point. By default is in this point. You see that this red point here, this is the gate. But I don't want to inject from this point. I want to inject from this side. So what I'm going to say is, okay, I'm going to add this point here as a gate. So if you click, okay, if you click in the injection point, you have conditions, injection point, clamping force. In the injection point, if you click right hand, you will see this menu. Edit, hide, and delete. Delete it. So what we are going to do now is I'm going to edit the injection gate. So I'm going to edit and I'm going to put this point here as a gating. Okay, so if you click here, edit, the program says that you already have a point for the injection, but I don't want this point. So since I don't want this point, I'm going to.
In my case, I have two gates.
You have two gates because you didn't change the configuration, but it's fine. You can keep this configuration. So remove both and click the one that is in this side. So delete. You have right button. You clear. You delete the point, and then you click directly here in this point. You see?
Yes,
If you click here, now we have this point as a gate. You can use any point that you want, but in this session, I want you to put the point here on this lateral side. So after the indicating the point, you just click OK. Okay, so I already have defined the gating, the gate. Then the next one is the clamping force. But the clamping force, we can skip the clamping force because, well, no, let's define the clamping force. Right button and edit. Okay, clamping force, edit. Here, the only thing that we need to say is which is the direction of the clamping. If you see, this is my part. So the idea is that this is going to be a mole here and this is going to be a mole here. Ah, vale. Okay, so this is, we assume that this is going to be the opening. The opening direction is going to be the horizontal. Okay, so the clamping force should be in the horizontal because the mold, you see that the highest section is in vertically. So the clamping force will be horizontally. So the direction of the clamping force is this one. That is already defined by default. The program estimates that this is going to be the clamping force. Of course, this is going to be the case. So just click OK. We don't have to do anything, just to confirm that the SolidWorks is in the right direction. So we already have the injection and the clamping force. And the only thing that is missing is the settings for, well, the settings, no, the mesh and the settings, two things. So first is the mesh. As you can assume, this is a program that the simulation is based on finite element analysis. Okay? So we need to create a mesh to do the analysis. So the mesh is here in the last option. So if you click right button, we will create a mesh. So we create a mesh. And here, the only thing that we're going to do is click create, because I can define the type of the mesh. I can create a refinement of the mesh, but we are going to skip all these details. Okay, this is a very basic course. So the idea is that I want to create a mesh by default. So a mesh by default is just to click here, create. And we click here, create, you will see this is the mesh that we have for the analysis of the part. So with this, we can click OK in this menu, and we have finished the creation of the mesh that is necessary for the analysis. And every time that you change something in the design of the part or in the gating of the part, you have to remesh the part. Okay, that's important. So let's click here OK.
Even if I am changing the runner and anything.
Yes, You have to remess.
The gate, and you have to do the
Yes.
image. Okay.
Actually, when you change something, you will see that there is a pop-up saying you have changed something, you have to remess. It's going to be
Okay.
indicated by the program. So that's why I'm doing everything, and the last part is the messing, because if I mess first and then I put the gate, I have to remess. Okay, so that's the idea. So now we have, you see, you should see something like that. If not, you can go here to SolidWorks Plastics, and you can show, there is an option here that is the mesh, to see the mesh or not. So I like to see the mesh, but if you don't want to see the mesh, you can hide in the mesh. But in my case, I like to put the mesh here. So everything is done. So the only thing is the settings. So the settings is here in the unit. When you click right button with the unit, you can change the polymer. That is not the case because we have already defined as ABS. But the first one is settings. I guess that you have settings or something like that. So if you click in the first one, that is settings, you will be able to change injection temperature, mold, the temperature of the mold, well, many parameters that are very important. So let's click here in settings, and you see all this information. We have the material, that is ABS. We have the temperature of the injection. You see 240 was the same value that was in the material parameters when we selected the material. So you can change that if you want. I want to inject to 250, so you can change here. Or the molding temperature, the mold temperature. Here you can say that you have a heating device and you are going to inject with a mold at 70 degrees. Okay, so you can change this temperature here. Okay, so in our case, we're going to keep all by default. The temperature of the mold and the material we are going to keep by default. And then we have here things that are also interesting. The first one is the time. If you remember, I told you about that if the time is very small, the pressure is too high. And if the time is too large, the pressure is too high because the material is the viscosity is very large and it's almost frozen. So there is an optimum time for injecting. Okay, so here, if you click automatic, the program will give you an estimation of the best time, of the optimal time for this part, according to the weight of the part and the average thickness of the part. Okay, so we can keep that value, or we can do some simulations to check which is the best one. So we can keep the automatic in this case. But if you click define by the user, you can say that I want 5 seconds, and you click here 5 seconds, and the injection, the filling time will be 5 seconds. But in our case, by default. Then we have the maximum injection pressure. This is the pressure that I told you at the beginning when we talk about the machine equipment, the injection equipment. I told you that there are some machines that can be 200 megapascals, 150, or so on. We can keep here as an example 100 megapascals, but the normal way to working with that, with this option, is to see my real machine. If my real machine is 200, I will write here 200 megapascals. That depends on my equipment. This is the change between filling and packing. Here we are going to put 100%. That means that after filling the cavity, I'm not going to change to the packing stage. In some cases, maybe here is interesting to write maybe 95. That means that when it's missing 5% of filling the cavity, at that moment, I'm going to change to the packing stage. Sometimes they say that for equipment, this is better because you don't go to the extreme points or whatever. I don't know. Here, usually it's 95 or something like that. In this case, we're going to write 100. That is the by default. By default, we're going to say that after filling, totally filling the cavity, I'm not going to change to the packing stage. Okay, that's the meaning of 100%. And here is when we are going to say that the mold is incomplete, that is a short shot. This is something that depends on the material. In this case, for ABS, 105 degrees means that you are not going to be able to fill the mold. So if the program sees that you have 105 degrees Celsius in the material, that means that it's almost solidified and it's finished the filling stage. So we can keep all this by default. You see that I'm not going to change anything or everything by default. And here is where we can change the profile. I told you that if you use a profile for filling, it's better than you keep a constant profile. So you can simulate the benefits of a profile here in this icon. Okay, I'm not going to do that because this is like an advanced topic. So I teach that in my courses, but I'm not going to teach you this here because it's quite complicated. So we can skip the rest and so keep all these values and click here OK. Okay, so it's by default. So the idea was to open the configuration, the settings, and click OK because we haven't changed anything. Okay, so with this, everything is done, so we can launch our first simulation. So to run our first simulation, we go to the top of this menu and right button, and you see that there is a running menu. So it's a running menu, and you have a filling stage. It's only filling because I changed the type of simulation for filling. If the type of simulation is different, you will see different options. But the idea is that just launch the filling simulation. So run, and you can click here filling. And after clicking this, you will see a screen. You will see a screen where there is some calculations, and we will see later with colors the results. Okay, that takes maybe 30 seconds or 1 minute, maybe, depending on the computer. My computer should be faster, but let's see. And then we can see the results. Okay, so you see, this is the results. So you see there is a menu where you can see many pictures about the results, the temperatures, the pressures, the shear stress, the sigma marks, and so on. So this is a very basic running filling stage, so you can see some results. So I don't know if you have been able to reach the.
Actually, yes, I got the same, yeah, same results as
Okay.
what you have done.
Okay, perfect. Then there was some of you that say that you had two gates. Probably it's going to be different the results because even if you change to one gate, I think that the configuration was different. So maybe it was smaller. So maybe you have some different results. But anyway, the idea is to see how works the SolidWorks plastic add-in, and now we can see some results here. So you can see here the first is this traffic light here. You see that we have three colors: green, yellow, and red. This is basically for the pressure, the injection pressure. If you remember, we said that we have 100 megapascals, the maximum value of my machine. And you see here in this text, it said that the maximum is 54.8 megapascals. We can see exactly the same here. The second graph is pressure at the end of filling. If you click pressure at the end of filling, you will see that the maximum pressure is 54.8 megapascals. That is just at the gate. Later, if you go to the right, the pressure is lower because it's at the end, totally at the end of the part. When the material reaches this value, it's finished the filling stage. That's why the pressure is almost zero. But at the beginning, the pressure is too high. So the pressure is 54 megapascals. So it's yellow because the idea is that this value should be half or lower than half the maximum value. So the maximum value is 100 megapascals. So to have a green color, the maximum injection pressure should be less than 50 megapascals. And the reason is that here, if you see, it's still missing the sprue, the runner system and the sprue design. So if you add the sprue and the runner, this is going to be higher. This is going to be maybe 70 megapascals or something like that. That's why it's yellow. It's saying that after adding the runner and the gate and the sprue system, you are going to be close to the maximum, that is 100. If it's red, it's because you are already in 70, 80, 90, or 1 megapascals. So red saying that when you include the runner system, you are not going to be able to inject this part. And in green is that there is no problem with pressures. Okay, so that this is these three colors basically are because of pressure. So things to see here. If we click here in the first one, the filling time, you can see the pattern filling. If you go down, you see the animation and you click play, and you will see how the part is filled. Okay, so we are filling with this pattern. So you can see that here it's slowly and here go faster because it's a smaller section and then goes a little bit slower. So this is what I told you about uniform front flows and so on is about that. You have to see that here it's accelerated, here it's lower. So these changes makes that maybe we have some warpage issues. Okay, so this is something to see. So what more here? Okay, here we have the welding lines. The welding lines here, you see, if you click welding lines, it's below the text. You see that here we have all these welding lines. Okay, so these welding lines, it's because the front flow will collide two front flows. So at the end, you have a welding line. So this is a very bad design or a very bad injection process now, because we will have welding lines in this part that is critical part. Okay, so this is just for checking the results. We also have here air traps. So if you click here air traps, you will see that these are the bubbles, the air that we need to remove from the mold. So when we design the mold for this part, we need to create some escapes for the air. So the air should escape in this part of the mold because are the last part that is going to be filled. So this software help us to see where are the welding lines, where are the air traps, and other things. Okay, to check the pattern filling and so on. So we can also see here one important that is the shear stress. The shear stress here, something like shear stress should be in your program. You can see the maximum shear stress. If you remember, I told you before that in the material properties we have a option, we have a characteristic that was 0.29 megapascal was the maximum. Okay, 0.29, and here in the simulation, it says that the maximum is 0.28. So in the material here is reaching 0.28. That is less than the maximum of the material, that is 0.29. So perfect. This in that case we are within the specification of the material. Okay, so this is fine. So we have the filling time, the pressure time, and there are other things to check that if you want, you can do it later and see if it's something that could be interesting for you. Okay, and another option that is interesting to check is the clamping force that we need. So we are injecting this part and we have a clamping force. We need a clamping force. We need to keep the molds close during injection. So which is the clamping force that we need for injecting this part? So it's not here in these results. So this is in another menu. So what we're going to do now is click here, okay. So we finish the reading the results. and we are going to open another one that is here. In results, you see, you click here, you have other options. You have a report. You can create automatically a report. So the program will create a report for you with all the pictures that you need. And we have here the results of filling. That is exactly what we have seen. So if you open this, you will open again the plots, the previous results. And in the middle, we have something that is called plot XY. So if you click here, plot XY, right button, and you click visualize, plot XY, you will see the graphs that are interested in terms of clamping. So if you click here, you will see, this is the pressure during the injection. Remember that I told you that during filling, we are increasing the pressure up to filling the cavity. You see, this is filling, and after the filling, we go to packing. But packing is not still simulated because I changed the study to only filling. So here you have this menu, so we can click pressure, we can keep also clamping force. If you click clamping force, you will see that the clamping force reaches the value of 250 tons. So this is a lot. Okay, you remember the machines that we review that were Chinese machines was the clamping force was around 100 tons. Okay, so this part is quite big, and the clamping force at the end is quite large. So we need to create a clamping force of 250 tons. If not, we will create a flash. We will create a important problem in the part. Okay, so this is important to check. And here we have also other options. We can check the temperature and the pressure of any point in the part. So you see here, I can click in any point here, and I can see the temperature. So if I click a point, after clicking a point, I need to click here add. You see, this is the pressure of this node. Can click another point and click add, and I can see the pressure of this point. Maybe now here and add, and this is the pressure at this point. I can check the pressure and the temperature. You see the temperature at the beginning is 52 because this is the temperature of the mold, and then when the material goes and fills this part, the temperature is around 240 degrees Celsius. Okay, so here we can check the temperature of the part during filling. Okay, so this is more or less the idea of this part. We can click OK, accept, and we go out of this menu. Okay, so if you want to retrieve the results of simulation, we can go here to the results of filling, and with right button we can click read, and with right button you click read, and we can go again to review the same okay, the same results of like before. Okay, so this is just up to you, so you can check all this. Okay, so let's see if this was the first part. I have something that I'm missing. So this is to put the gate, the clamping direction, the filling running, about the colors, some results here, the shear stress that is important to be according to the specification of the material, and then some plots related to XY plot. Okay, so more or less this is the very basic understanding of filling, of the filling states with SolidWorks. Okay, so I don't know if you have any question about this part. So just feel free to ask me whatever, and if it's fine for you, what we can do is to move to the exercises. That is where you are going to work by yourself, and you can ask me whatever you want. So if we do that, the idea is that you will have some time for you, and after 5-10 minutes, I will do the solution with you. Okay, I will share the solution of the exercise. I will do it here with SolidWorks simulation, with SolidWorks plastic, so you can see the steps that we need to do it. But basically, what you have to do is exactly the same. You see here, I'm going to show you the exercises. So the exercise, computer session 1. Here, so in 5-10 minutes, I will solve the first exercise. If you finish the first exercise because it's quite simple, just move to the second one and so on. So we can see if at the end more or less you have the idea of using the program for the simulation. Using the predefined injection molding time, you remember that the predefined, okay, first the configuration is predetermined, so this is the first one, good. So now we are using the molding time, the injection filling time by default. Okay, so we don't have to change the settings for this case. And what we have to change is the gate. So from the position one is this one that is from left side, and position 2, I told you that it's in the middle. So use 100% filling packing switch point. Remember that this is that we are going to change to the packing stage when we have filled 100% of the mold. This is what we have done before. So all the results that we have done before is the position 1. So we can directly write here the results from the previous simulation. So if I open here, this is the simulation with point 1 from this side, 100% filling packing switch point, and the filling time by default. Okay, so here they are asking us about the maximum pressure and the maximum clamping force. So the maximum pressure is here. You see that the maximum pressure is 54 megapascals. So we can write here that it's 54 megapascals. And the clamping force. Remember that the clamping force is not here. We have many information with these results, but the clamping force is here. Okay, so when we open the plot XY that we did before, we can see different points, the pressure, the temperature, but we are interested in the clamping force, that is this curve. So you see that this curve, the maximum clamping force is at the end of the filling stage, that it's around more or less 250 tons, more or less. So this is 250 tons. So 250 tons. Up. Okay, and now the question is, okay, let's see what happens if we gate in the middle. So if we gate in the middle, we need to go here, and we are going to remove this point. So I'm going to say that I want to edit the injection point. I want to remove this one, and I'm going to use this point to more or less be in the middle. This is the point 2. So I click OK, and the program is saying that we need to remesh the part. So good, we go here, and we're going to remesh the part. Create mesh, and all this by default because we are not paying attention to the details of the mesh. So it's done. The material is the same. The only thing that we have changed is the gating, that it's here. So now we can run the simulation. We are going to remove the problem that we need to change. Maybe it's going to be a problem because I didn't change the settings, so maybe it's not going to. Let's see if it works. Yes, it seems it's working. The settings are the same like before, so we didn't change anything. We only changed the gating. And now we can see that let's see. You see that now it's green. That means that the final pressure is even lower than 50 megapascal. You see, the pressure at the end of filling is 38 megapascal. So here we have 38 megapascals. You see, it's lower, just changing the gating point. So that's because we are reducing the length of the flow of the front flow. So the pressure is lower. So it's a more efficient process because we don't need to inject with a higher pressure. And now let's see about the clamping. What happened with the clamping force? If we go to the XY plot, we can see the clamping. Here, exactly the same like before. We need to click clamping force. And here the clamping force, you see that reaches, there is something here that changed a little bit. We should see what happens here. But anyway, let's assume that this is around 240. Okay, maybe this is because of the settings that we didn't change, but it's 240. So we can write here that this is 240 turns. So lower clamping force and lower injection pressure. Okay, if we change just the gating, so that's important characteristic here. Okay, so this is done. So we have done this one, and let's see the second one. The second one is just to change the workpiece. I mean the material. So from ABS, we are going now to put polycarbonate. So we go here, and the only thing that we have to do is change the material. Remember that the material is here in the injection unit. So with right button, we can change the polymer. Okay, so we can change the polymer here, and we are going to change from ABS to a generic polycarbonate. The gating is at position 1, so we need to change the gating again to the left side, and 100% filling and packing switch point. So let's do it. Let's change the material. We click edit polymer, and we're going to use a generic polycarbonate. So here, remember that we have different databases. So we are going to put here predetermined databases, not for vendor. We are going to put now by family, by materials. And here I'm going to look for a polycarbonate. Here there is ABS with different materials, and polycarbonate, it's here, 72. So the polycarbonate, you have many different vendors, but the first one is a generic. So we can click here the generic polycarbonate. Okay, the only thing that we have to do is change the material here in the unit. Okay, so we will click OK. This is something that we have seen before in the first computer session. And the only thing that we need to do now is, besides changing the material, the gating, because the gating, we said that this is not in the middle, it's in one side. So we click edit the gating, we remove this one, and we put again the first point from that side. And we click OK. We should remesh, we know that. So after putting this, we remesh, that we go here to the mesh, and we say create a mesh. Everything by default. And after the mesh, we click OK. So we have changed from the first example the material and the point, the gating point. We can check the settings just to be sure. So the settings are with right button here, settings. And this is the material for polycarbonate. You see the temperature for injecting the polycarbonate is 305. It's higher than ABS. Okay, the mold is also higher. So we are going to keep all this by default. Okay, so this is generic polycarbonate, the recommendations of generic polycarbonate injection. So everything is defined, so we launch the analysis, filling analysis. We are going to remove the previous results, okay? We are fine with this. And now we're going to see what happens here. So it's 60%, at the 70%, the pressure is 52, and 80% the pressure is 58. Okay, these are all the calculation that it's done by the program, and after finishing, it's closed, and we can see the results. See, so this is the results. The time here is 4 seconds, 4.5 seconds for filling the cavity. And the pressure you see here is 67.4 megapascals. So if we go here, the maximum pressure with polycarbonate is 67.4. So this is 67.4 megapascals. In the injection with ABS, that was the first case, was exactly the same like before. So this is 54. It's the same like before. Okay, we don't need to simulate again because this is exactly the same like before, 250. Okay, this is exactly the same like this this case. This and this is the same. And now we need to check the clamping force. So the clamping force is exactly the same. We go out of the results and plot XY. Plot XY, and we will see clamping force. So the clamping force here, you see that we reach even 300 tons. So the clamping force, 300 tons. So here we have 300 tons. So we can see that for exactly the same part and exactly the same gating changes with this difference just from the change of the material from ABS to polycarbonate. Polycarbonate is more difficult to be injected. ABS is quite simple. Okay, so this was the first example, the first exercise. So we can see how influences the gating here, how influences the gating, and here how influences the change in the injection material. Okay, so now we can do exactly the same, 5-10 minutes, so you can try to work with this exercise. So in this case, configuration área espesor reducida, so you have to go here. So you need to go to the configurations and click área espesor reducida, that is the first one. Okay, so you click here, the first one, and now you see here what happens. Now we have here a reduction of this area. So the thickness of this region is smaller than the region that it's around it. So let's see what happens if we have a part something like that has this feature here in the middle. So we will have some problems to inject this part. So that's the purpose of this exercise, to see what happens with this type of designs. So we go to plastic, and here you have to do exactly the same like before. So you have to select the gate is position 1, so the gating is this one, exactly the same like before. The material is a low density polyethylene, a generic low density polyethylene, so you have to select this from the list. And that's all. So the only thing that you have to do is these two. And in the settings for the injection molding, be sure that you have 100% filling and packing switch point. So with this, you simulate the process. Here we have exactly the same problem like before. By default, it's all the simulations. So we can edit here and say that I don't want all. I only want to do the filling simulation. Okay, so only filling. I don't need packing and the rest. So just select the position, the gate, the material, check that it's 100%, and run the simulation. And you will see that the pattern here is not good. So we need to write here which is the problem that we have. And then you have to check the shear stress. will happen with the shear stress in the simulation. Remember that we showed that before. The shear stress, you have to look in the graph, which is the maximum shear stress. And then here there is a question that how can we reduce the shear stress? So what are the parameters that we can change in the simulation to reduce the shear stress? So you can think about that. Imagine that one option is to increase the temperature. So you go to settings, increase temperature, and you will see if you reduce the shear stress or not. Okay, this is a little bit more complicated, but at least the first two should be something done very easily by yourself. Okay, so try to work on that, and in 5-10 minutes I will solve this exercise for you so you can see if you are on the good path or not. Okay, so let's see if you can do it. Okay, so this is the exercise number 2, área espesor reducida. I think that I changed, I already changed that. Okay. Then the injection point should be position 1, that is this left side. The material, so we need to change the material. Remember to change the material, we go here, and we can change the polymer. So edit the polymer. And now in this case, we need a low density polyethylene. So low density polyethylene is number 25. There are a list of vendors. So we are going to use the first one, that is a generic one. Okay. So now what happens, this is on the other side of the part. Okay, this is an error, this is another side of the part, which is the name of this phenomenon. So let's mesh the part first, and then we'll simulate the process. We create the mesh. Okay, by default, the injection point is here. The clamping direction is already defined by the previous exercises, so we don't need to change it. So just we can change or review the settings. Okay, so in settings we can see now the temperature for injecting low density polyethylene. It's even lower than ABS or polycarbonate. It's 220. This is a very easy material for injection, and we keep the rest 100% the filling packing chains, and we assume that our equipment, the maximum pressure is 100 megapascals. Okay, so let's click OK, and let's run this analysis. Okay, so it's almost done. Okay, so you see that it's green color, so that means that the part can be injected below the half of the maximum injection pressure. Actually, here you see that the maximum pressure is 23 megapascals, and our machine, injection machine, we assume that is 100 megapascals. So we have more than enough pressure for injecting this part in low density polyethylene. We can compare this value with the previous one. You see here, polycarbonate was 67 megapascals, ABS 54 megapascals. So we are working with low density polyethylene. The pressure is smaller, okay, because the material is easier to be injected. Okay, so the question here is what happened with this new design that we have a reduction of the area here. So if we click in the time of filling, and we click the simulation of to see the pattern, you will see that everything is fine. And then what happens here? You see here We can even reduce the speed. I think that this is the speed, yes. You see that this is going slowly, then here will be an increase, and then we'll see that here we have a problem. See that? Here it stops, and then goes from the easiest path, that is the thicker area, and then at the end what we are going to have is a problem here, because we will have air trap here. We will have an air trap here and a welding line here. Okay, so we can stop here and we will see welding lines here that it's very bad because of this, because the front flow is split in two, and also we have air traps. You see this air trap. How can we remove this air trap? Because these that are in the turrets are easier, but to remove this, so we have a clear problem here of pattern filling. So this is what is asked here. So analyze and what happens at the other side of the part, which is the name of this phenomenon. So if you remember, we saw that in the theory, and the problem is the arrays tracking effect. The melting polymer tries to fill the easiest region, and after filling the easiest region, that is the thicker one, tries to fill the thinner one. So that is the race tracking problem. So we have a race tracking problem here because the front flow tries to fill first the thicker region that has less resistance. So here the solution would be that we have a race tracking problem. Race tracking problem. Let's race tracking issue. Okay, so that's the problem, and we need to change the design because this is not a well design, or at least we need to reduce the thickness of the region that it's around this reduced section to avoid this phenomenon, or at least to minimize this phenomenon. Okay, so the next question is, which is the shear stress during the injection process? So let's see the shear stress. Remember that the shear stress is here. I showed you before in the computer session 1, it's here. So you have the English language, so you will see that it's this one, shear stress. So you see shear stress, you will see which is the shear stress of this. I'm going to remove the air trap. So you see that the shear stress is 0.12 megapascals, and it's around this part, 0.12 megapascal, that it happens here. We can even put here 0.1, and you will see that all this part that is in blue is 0.1 megapascals or less, but up to 0.12 it's this region. So this part has a too high shear stress, that is 0.12 megapascals. So here, which is the maximum shear stress? 0.12 megapascals. And now the question is, which is the maximum that it's admissible by the polymer, by this material? So I show you that you have to look that information here in the databases of the material. So if you open here the polymer, where would you choose the polymer? Here we are in the low density. Okay, here we are here in the low density polyethylene. Remember that this is in this tab, material parameters. If you check material parameters, we can see the temperature of the material, the temperature of the mold, the recommendations, and here we have the maximum shear stress. So the maximum shear stress is 0.1 megapascal. So here, which is the maximum? 0.1 megapascal. And in our injection process, we have seen that we reach 0.12 megapascal. So although it's not too much, it should be recommended to try to reduce this shear stress. And this is the question 3. The question 3 is, okay, how can we reduce the shear stress during this injection molding process? So there are different solutions. So if you want to reduce the shear stress, one option could be to increase the temperature of the injection. Temperature of injection, increase. Why? Because if you increase the injection temperature, you are making the polymer less viscous, with a less viscosity. So if the viscosity is lower, the shear stress is lower. Okay, so if you increase the temperature, you will have a higher temperature. So the other thing is to increase the temperature of the mold. Exactly the same. So sorry, to increase the temperature, also increase. So if you increase the temperature of the mold, you will reduce the cooling of the molten polymer when you are injecting the material. So if you reduce the cooling, you increase the viscosity. Sorry, you reduce the viscosity. Okay. So the idea is to make the polymer with a less viscosity. So if it's with a lower viscosity, you will reduce the shear stress. Okay. There are other, for instance, the speed, the injection speed. You can reduce the speed. You can reduce the injection speed. So if you reduce the speed of the injection, you will reduce the shear stress. But if you reduce too much, the cooling effect will be the opposite effect. So you will make higher the shear stress. So there are some possible solutions. So the idea here is that we're going to try to see what happens if we increase the injection temperature and the mold temperature. Okay, and we will simulate again and we will see what happens. So let's see if we change. Oh, sorry. Let's see. Oh, it's fine. I'm going to change the simulation and we see if we are going to improve the shear stress. So I go here to settings. Now, and here in settings, I'm going to increase the injection temperature to, instead of 220, 240. And the mold, let's see that instead of 40 degrees, I'm going to increase to 60 degrees. Okay. So let's see what happens if I add these changes in the parameters. Click OK. And now everything is the same. I don't have to change anything. So I change the settings and just we can run again the filling analysis. Okay, so what I've done is to put here, instead of 220 degrees Celsius, I put 240. And instead of 40 degrees in the mold, I increase to 60 degrees in the mold. So doing that, the shear stress is now, let's see which is the value of the shear stress now. Okay, let's see if we have been able to reduce or not the shear stress. So this is the final. We can see that it's exactly the same. Okay, the problem is exactly the same. So we have here a acceleration of the movement of the mold flow, and here we have the problems here. Okay, let's see the shear stress. So the shear stress here is this one. You see here now the maximum. We can click here 0. So now the maximum is 0.09, almost 0.10 megapascals, and it's let's see 0.07 for instance, and it's again here in these walls, but now it's not 0.12. Now it's 0.10. That is just what I need. So doing these changes in the settings of the injection, we have been able to reduce from 0.12 to 0.1 megapascal. That is exactly the maximum admissible for the material. So for this part, that could be a good option. Remember that this is an option just to avoid the shear stress, but we have an important problem here, that is the air trap and the welding lines that we have here because of the reduction of the area in this part of the injection of the cavity. Okay, so this is something that we need to solve. This is not the case. We are now just changing the shear stress. Okay, so this was an example also how to change, how we can improve the quality of the part or the shear stress in this case, and also taking a look to issues that we have, just taking a look to the pattern fitting. Okay, this is what we have done here in this exercise. Okay, so if you have any question for this exercise, I don't know if you have been able to do that. Maybe it's difficult because it's the first time maybe for some of you to work with this software, but I think that it's not complicated. Okay, so any question or any comment that you want to add, or we can continue with the next exercise?
It's okay for me.
Okay.
And also for me, actually, it is okay.
Okay, thank you. Thank you for the feedback. Okay, so now we can move to the next one. Exactly the same, 5 minutes. This is quite simple. The only thing that you have to do is change to this configuration that is here. Remember, now is the last one. So we are going to change. You see here, this is the pattern that is called the grid. So we're going to change this grid. Instead of being vertically, we're going to change to this one. Okay, horizontally. And now we are going to simulate this one. You see that in this case for me, I don't know why I lost the add-in, the plastic add-in. So you can click here, new study, so we can do the simulation. Okay, I don't know exactly why. Maybe it's because by default I have no simulation in this part, so that's why it's removed the add-in. But anyway, if you change and you don't see the plastic tab, just click here, new study, in the tab that is SolidWorks plastics, because it depends on your add-in. So look for the add-in that is SolidWorks, and then click here, new study. So here in the new study, this is what I told you before. You have two options, solid and cell. Solid is if the part is thick, so you need to do a, instead of it's like a 3D analysis instead of a 2D analysis. We are doing a 2D analysis here. So when the thickness is small, you can use cell. If the thickness is big, you need to move to a more complicated analysis that is solid. So we are moving to cell because we are assuming that this thickness is small. Okay, so shell, and now we already have the plastic manager. Okay, so now the exercise is use this material ABS from BASF. This is from BASF. Remember that you need to go to BASF vendor, manufacturer. You need to add the gate in position 2. Remember that in position 2 is in the middle, so we need to put the gate here in the middle and analyze what happened with this pattern. And you can write here what do you think it's, if it's better or not, this design with this configuration with this grid, or it's better the other grid that is vertical. Okay, so this is we show that in the theoretical part. Okay, so that's very simple. So 5 minutes if you want for this, and then we can go to the last one. Okay, so 5 minutes for this example, that is just to change the configuration, the gate, and the material, and launch and run the simulation. Okay, so just do it in 5 minutes and I will show you the results. Okay, so we have changed the configuration, and now exactly the same like before. By default, I have here two types of simulation. I don't want to have a filling and packing. I just want to have filling. So I change, and I'm going to use only filling analysis. So I have to change the material to ABS. So material, remember that is in this part. So edit polymer. And in edit polymer, I'm going to use ABS generic. That is almost the first one. In my case, you put by family, ABS, the first one is the ABS generic. Sorry, that is not the generic, it's 6003. So we go down, if number 26 is ABS 6003 from BASF company. Or we can look for this in classified by manufacturer. So I select this one, ABS, and now the gate in position 1. I need to put the gate here. Position 1 is this one, so the gate is, oops, let's see, here. Injection point. So injection point gate here. So I click OK. So I have the gate, the material. Now we need to mesh, create the mesh. Remember that there are many parameters here, but we are going to use the defaults. Okay. And with this, the only thing is to check the settings. So the settings, we can see that the material is exactly the same like the first analysis that we did. ABS 240, 52, automatic 100%, the filling packing stage. So all this is exactly the same like in our first simulation analysis. So we click here that it's everything it's okay. So we can launch the simulation. Run filling. Up. I don't know why I lose the injection point. So injection point is here. And then we need to remesh. I don't know if what happened. Sorry, I made a mistake here. I think now it's fine. Let's see if it works. Okay. So we are now analyzing the injection. Is the same parameters like than in the first case, but the only thing that we have changed is the design. The part design is different because this grid, these slots that we have here are horizontal and not vertical like before. So you, of course, that you already know what's going to happen. Here it's horizontal, so the front flow will go from the left to the right, and there is no welding lines. It's going to be some melt lines maybe here, but it's going to be very good quality. So if we change to the first design that the grid is in vertical, we will have a large quantity of welding lines. So this is not a good design. So this is a better design. So here it said that we have a problem. It's red color, and here if you read in my case, I don't know if you have the same, but in my case it said that we have too much clamping force. We need too much clamping force. Probably the problem is that we haven't said which is the direction of the clamping force here. So we can omit this message because it's just because we didn't say which is the direction of the clamping unit. So we see here that if we play the simulation, we can see that there is no problems here. So it's going to that part, and we can see the welding lines. You see, there is no welding lines here. There is no welding lines, and the only welding line that we have is here because the front flow splits in two, and then there is a collision of the front flows here. So this is the welding line that we have. It's normal because it's a hole. There is nothing that we can do. But here we don't have any welding line in this grid. That happens in the previous design. So the result of this, what are the advantages of this design? So there is no there is no welding lines. No welding lines. Welding lines. Let's see at the grid. At the grid area. Okay, so this it's a better design, of course, than having the grid in vertical. Okay, so that was very simple. So let's see the last one, and after the last one, I will show you very fast the basics of the packing analysis. Okay, so try to do it this by yourself. It's going to be just 5 minutes because it's quite simple. It's just to change the material and launch and run the simulation. So it's going to be very fast. So you see here you have to put the espesor reducido. This is the second configuration. Okay, so you click the second configuration, and after that you can complete this exercise. Select this material and this position, and then you have to see what's going on, what happens, because we have an important problem here in this last exercise. Okay, so you can try to do it in 5 minutes, so we finish this part.
I have a question.
Yes.
Regarding the clamping force, only we have to select one face only? We cannot select different faces or multiple faces?
Actually, if you see here, I changed that. If you don't select the surface and you click here, now it's not open, but if you click the results, the XY plot, you will see the clamping force in the 3 direction, X, Y, and Z. So you can
I
have
mean,
the forces, the 3 forces.
I mean, can I have in the design itself different faces to select, or only one face I can select?
But if you use this part, that
Yeah.
is, you need to select only one surface, because you are when you are actually when you are in a mold, there is a main the parting plane. The parting plane is the main plane where you are opening and closing the mold. So basically you have only one plane. So you have here to select one face or one plane, but only one. If you select different planes, I guess that, I mean, it's not possible. You have only to
Not
select one
possible,
plane.
yes, to understand. So this it depends on the design itself.
Exactly, because but usually, I mean, this is like basic rules for creating a mold. Of course, that if you have a part, your parting plane, your opening plane is going to be always the plane that has a bigger cross section. So it doesn't make any sense in this case to have a parting plane in the other in perpendicular to the one that we have selected. It doesn't make any sense. So this is like a basic rules for mold design. So the biggest plane, is the biggest cross section area. This is going to be your direction of opening, and then your direction of clamping force.
Okay,
Okay.
thank you.
Okay. Okay. So try to work with this exercise. Okay. If you see, by default, I have two gates. So remove these gates and put the gate here on the left, because this is the question here. Put the gate at position 1. That, remember, that is this extreme point, the left side, and analyze, and we will see what happens with this design, and then we will try to do something to improve this design. Okay, so try to do it, and later we will work with computer session 2. I will do it fast because it's not too much time, but it's going to be just an overview of the packing stage. Okay, I will show you the packing stage later. So finish this exercise, and then we will see. Okay, now it's fine. Are you
It's okay now.
okay? Okay, I'm going to explain you what I did just fast. Okay, I changed the type of simulation. Okay, I add here ABS. Then I add here the gating in this point. I remove the other 2 points, and then I create the mesh. Okay, and after that, I just run the simulation. So this is what is given here in in this exercise. So if we go here to the results, we can see what happens here. You see, if we click the animation, you see that it's not possible to fill the part. You see that is the front flow is going here, but at the end it's not possible to fill totally the part. So which is the name of this problem? This is called a short shot. I told you about that in the theoretical part. This is when you have no enough pressure to fill the cavity under the conditions that we have defined. The problem is that in this configuration that is the espesor reducido here, we have reduced the thickness of the part with respect to the previous one. So with this, if this part, the thickness is small, actually the thickness here I think is 2 millimeters thickness. Maybe before, maybe it was 4 millimeters the thickness of the part, and now it's 2 millimeters. So since the thickness is smaller, we need a higher pressure for injecting this part, and we don't have enough pressure. We can open here the plot XY and we can see the pressure. You see, this is the clamping force, remember, and this is the pressure. So we are increasing the pressure up to 100 megapascals. We can't increase more than 100 because this is the limit of my machine. Remember that in settings, we said that our machine is able to reach 100 megapascals for the injection and not more. So at the end, we are at the maximum, and even at the maximum, we are not able to finish the filling. You see here in the simulation. So this is a good example of problems that we may find in the injection because we don't have enough injection pressure. Okay, so here, which is the problem? It's a short shot. That means that we can't complete the cavity. We can't fill the cavity. So a possible solution, which is the possible solution? Because a possible solution is to add more gates. Remember that I told you about that. So if we add more gates, we will reduce the pressure that we need for the injection process. So you can test that instead of having one injection point, maybe we can remove this and add this one and this one, for instance, and we can add 2 points. We can add 2 gates. We need to remesh. Remember that when we change the gates, we need to remesh. And now we can launch the same simulation. And under this configuration, we have 2 gates, so it's going to be easier to fill the cavity without changing the design and without changing our equipment or injection machine. So the only thing that we have to do is to redesign the gating system, the runner system. So you will see that we have reached also 100. We are also in the limit 100, but we have improved you see here that we can see that now we are injecting from 2 gates and we are able to fill all the part. Okay, this is not still good enough because we are in a red color. That means that we are reaching 100%, 100 megapascals, and it's still missing the runner system and the sprue system. So maybe we need another one. We need 3 gates for filling this part under this thickness. Okay, so but we have seen that at least 2 could be enough, or maybe 3. Okay, maybe 3 gates, we can say here. Okay, so this is the solution of these exercises. So any question that you may have from this part, that is the filling analysis, or anything that you want to ask, and then we'll move to computer session 2. So anything that you may want to say or something? Okay, so if you don't have any question, let's see the last part of the session. So the idea here is to analyze the packing. Okay, the packing stage. So remember that the first stage is filling, so we need to fill the mold, and the second step is to pack. It's the packing stage. So let's see. I'm going to write here. Let's see if I can write. Okay, maybe I can write here. So remember that this is something like that. We have, this is the time, this is the pressure, and remember that we have first pressure, and then we change to something like that, and then we do something like that. So here is filling, the filling stage, and here this is the packing stage, and here this is the cooling stage. Okay, so this is what we have to write here in the program. Here in the type of simulation, we can say that only filling, or filling must packing, or filling must packing plus cooling. Okay, so this is where the options are. So in this case, we are going to use the filling plus packing. So let's see the part. Part is part one, so it's exactly the same like before. I'm probably we are going to use the predefined configuration. Okay, so I'm going to use the predefined configuration from the same part. So the computer session 2 uses the same part like in computer session 1. Okay, so we just put the predetermined configuration, and then here what we're going to do is analyze the packing stage. Okay, not only the filling stage. And for doing that, we are going to add a runner system. So we are going to sketch these lines to create a runner system. And with this runner system, we are going to use as a gate the runner system, and we will see what happens with the filling pattern and the packing pattern. Okay, this is what we're going to see in this session, in this part of the session. So let's see. We are going to let's see if we can see the planes. If you click here, you can visualize the planes. Okay, so I'm going to visualize the planes because I want to sketch here. I want to sketch the runner system. Okay, so the runner system is going to be, I think that more or less here. Let's see the session. Okay, here. You see, this is what we are going to draw. So I'm going to start the sketch with this tool. Remember that we have a sketch tool here. If you are a user of SolidWorks, you know that the sketches are here. So we are going to click sketch, and in the sketch, I'm going to use this plane. Okay, that is in the middle, because in the runner system is going to be just in the middle of the part. So I'm going to click this. So I'm going to put here, I'm going to do it a little bit faster because we don't have too much time. So you can just see what I'm doing, and that's all. And now we are going to write this sketch. Okay. Okay, I'm going to write this sketch. Okay, this is 1 millimeter, 100 millimeters, 80 millimeters, 100 millimeters. So I'm going to write here one line, another line, but and a second line here. And now I'm going to give the dimensions. So this dimension, okay, first is from 3.4. So this point is 3.4, And now, okay, yes, and now this is 1 millimeter. This is just an example of a runner system. Okay, so you can do it different. So this is going to be 8, and this is going to be 100. Okay, so this is a sketch, and now I'm going to use this sketch to create the runner system. That is this one that you can see here. So I'm going to click OK, and now I have this runner system. So now I need to complete the channel design with this sketch. So this is here, right button here. No, it's here in domains. In domains, if you click right button, you can see the channel design or runner system or something like that.
Can you just open the sketch for 1 minute?
Open the sketch.
Yes,
Okay, yes.
just for 1 minute.
Yes, this one.
Okay.
Okay, it's I use 1 millimeter is going to be, this is going to be the gate. Okay, then we have 100 millimeter that's going to be the runner. Then this is going to be the sprue well, 8 millimeters sprue well, and this is going to be the sprue. So this is the sprue well, runner, and gate. Okay, and this is something that has been calculated with some guidelines, but I skip all these details that are given in another course. Okay, fine.
Okay,
So
it's okay for me.
okay, thank you. So with this, we need to say that this is going to be my runner system. So in domains, in runner system, I select here I have some possible shapes for my runner system. So I'm going to start with a cylindrical shape, because I'm going to say that my sprue, the sprue usually are cylindrical, and you buy this from a vendor. Usually this is an insert that you buy from a vendor. So I'm going to use this shape, the circular. So I'm going to select this line as my sprue, but now I have to change the diameters. So here in the lecture notes, you have the diameters explained. It said that the initial is 3 millimeters and the last is 8 millimeters. So I'm going to say that this is 3 millimeters and this is 8 millimeters. And the other way. Okay. Okay, so we start with 3 millimeters and then we finish with 8 millimeters. Good. Then if I want to follow with the other design, I just select another line. So this line is going to be also cylindrical, but in this case, the last part of the sprue, that is going to be just a cylinder, and this is the sprue well, the place where the slag will be kept from the initial mold, front flow. So this is going to be 8 and 8 because this is just a cylinder. You see, this is a cylinder. So this is taper and this is a cylinder. And then we're going to use this one. So for this one, I'm going to use another type. That is a trapezoidal shape. So we are using conical, cylindrical, and then here I'm going to use a trapezoidal shape. So the values for this is 6. Let's see here. Okay, here 5.7, 8.1, and 6.8 of height. So here we are going to use the height is 6.8. The height is 6.8. The height in the second, you don't need to do it exactly the same. Okay, so I'm going to do it for you. Okay. Okay. 6.8, 6.8, and then it's 5.7, 5.7, 5.7, and the other is 8.1. 8.1. Sorry, here 8.1. Okay, so this is the, I don't know if I did something wrong because it seems that it's bigger in one part and the other. Height, okay, this is, I made a mistake here. Is 5.7 is the first one, this is 5.7. The second one is 8.1 and the height is 6.8. And then the second is 5.7, 8.1, 6.8. Now it's okay. Okay, so this is the trapezoidal one, and now the gate. The gate, remember that it's just 1 millimeter. This one. And the gate is going to be rectangular. And the value of the rectangular is 4 and 2.25 millimeters. So it's going to be 4 and 2.25, 4 and 2.25. Okay, so this is the gate. This is just to make you now that let you know that there is a tool here that is to design your runner system. Okay, and you can use cylinder, rectangular, trapezoidal shapes. Okay, so in this case we have defined the runner system, and now what we have to do is say that this is going to be my injection. This is going to be my runner system. So the injection point should be not this one. I'm going to remove this one. It's going to be this one. I'm going to add the material from this part. So this is the sprue well, the runner system, the gate, and then we fill the part. Okay, so with this, we have designed the runner system. We have defined the material. I don't think so. Material is going to be exactly the same like before, I guess. Okay, the material is low density polyethylene and default values. So low density polyethylene, we need to create the mesh. That's going to be a default mesh. Okay, so we have a default mesh, the injection point, the material, the cavities is created, the runner system, the channel design is created. Let's check the settings. Settings are fine, 100% filling and packing point. So I think that everything is done. So the only thing that is missing here is that I'm going to add both studies. Okay, let's launch only filling and then we will change to packing. Yes, because we need to explain packing. So filling. So now it's trying to calculate. Let's see if it works because, okay, you see, we are using the sprue system, the runner system, for filling this part. Okay, so you have seen here how to design the sprue system. Okay, you see that now we are in yellow because we need a higher pressure because we need to move the material from this small runner system. So now we need 55 megapascal of pressure for injecting this part. Okay, and we have here, you can see the simulation. You see that starts from the gate and then from the sprue well, and then we fill all the part. Okay, so this is what I wanted to show you for the first part, that it is sprue design. And then here it's the packing states. So the packing states, what we're going to do is analyze the gate when the gate is solidified. If you remember, I told you that the packing, we need to pack the material until the gate solidifies, the gate seals. So let's see this in this simulation. So the first thing to do is that now say that we want a filling plus packing. Okay, so now I want to analyze filling plus packing. Okay, yes. And after that, I need to indicate the settings for packing. So if we move here and we click settings, we have the settings for filling, and we also have the settings for packing. You see here, this is packing. So you click here packing, you will see two important values: the packing time and the cooling time, the pure cooling time. So here, if you see, let's see, I'm going to open here like if you see here is like, remember that we have something like that. We are going to have the pressure that is going up to the end, and here we are going to do something like that. Here it's filling, and here it's packing, and this is cool. Okay, and here we eject the part. We eject the part. Okay, so in SolidWorks, you see that at the beginning when we talk about filling, we said about the time of filling. This is the time of filling. That in our case, you remember, was around 5 seconds. Now we have to decide which is my packing time. My packing time is this time. And then I have to decide which is my cooling time. That is this time. Okay, so this is what we have to do here in SolidWorks. So here, if you see, you can change this manually, but if you put this, if you click in that icon, it's like it's defined by default by the system. So according to SolidWorks, SolidWorks thinks that the best packing for this part is 8 seconds. So in my here, that means that here is going to be 8 seconds. The packing stage is going to be 8 seconds. And then after packing, we are not going to apply any pressure, but we still clamp, we still close have the mold closed until 31 seconds. You see, this is the cooling time. And after that, we will eject the part. Okay, that's the idea. So this is according to SolidWorks. Okay, fine. So let's see what happens with this analysis. So we can run, and we're going to run both. So this now takes more time because we need to analyze filling plus packing. So you will see that now we need more time. Maybe it's 1 minute or something like that, the computing time. Okay, so it takes some time. So after doing that, what we can do is check the results from packing. So in packing, we have also some results. So we can see also the shear stress during packing, the sigma marks during packing, the pressure at the end of packing, and so on. Okay, so we can do exactly the same. After packing, we will see these results and check that all of them are fine or not. Okay, that's the idea of packing. And one of the things that we can do in packing is to analyze when the gate solidifies. You know that the gate is the first region of the cavity that solidifies, so we can calculate the solidification time using the XY plot. With the XY plot, we can see the temperature of the gate during the packing and cooling time, so we can see if the temperature is correct or not, or we can change these values in the simulation. So let's see that. Okay, let's see if it has finished. You see, it's still working. So we have the filling results, but we still the program is still working on the packing time, on the packing analysis. Now it seems that it's finished. So it takes 2 or 3 times longer than filling. Okay, has completed, so it close. So we have here the results of filling, but I want the results of packing. Usually it's here, packing. Sometimes I don't know why it's not shown. So we can click OK, and then we can go here and open results for packing. And now we are looking for the result of packing. You see, packing, filling, packing. So now we can see which is the shear stress during packing, which is the temperature at the end of packing, and whatever. Okay, so we have the result of packing. And now we can check the XY plot. So in the XY plot, we can see now the figure that I drew before. You see here, let's see if I can. Okay, good. You see, this is the filling. Here, exactly the same. The first step is filling, so pressure is increasing until we fill the total cavity, and then we have a constant packing. Here we have a constant packing, but the packing is in two ways, because the settings in SolidWorks by default is that we are going to pack 80% of the maximum pressure, and then we're going to pack 40% of the maximum pressure. And then here we start with cooling, and after 44 seconds, the mold is open and the part is ejected from the mold. Okay, so we have the filling and the packing. And in SolidWorks, we can still do another simulation that is warpage. Is the errors of the dimensions, if the warpage is important or not. So we have to decide to remove, or we have to change the mold or the gating system or whatever. Okay, so here we can see the temperatures. You can remember that we can add some nodes. So we can add nodes also here in the gating system. We can add here in the gating system this node. Okay, so we can see when the gate solidifies. So if we do that, we can go here and we see all the temperatures. So you see this 7, this is probably the gate. So the gate will solidify when we reach this line, the dashed line that is here in blue color. So when it's around 90 degrees, when the gate is at 90 degrees Celsius, we are going to solidify the gate. That it's around 12 seconds, you see? So from 4 to 12, it's almost 8 seconds. That is the value that SolidWorks has said that is the best for this part. So he did a good estimation, because at the end the gate will solidify around 12 seconds. So it's 8 seconds for packing. So this is going to be 8 seconds. And then here we can see also, for instance, different, you see the 9. So the ejection, the part can be ejected when 90% of the temperature of the part is below the ejection temperature, that is this one. The ejection temperature is around 80 ejection. So more or less around here is when we can eject the part, because almost everything is below 80 degrees. And it's what is done by SolidWorks, because SolidWorks says that the cooling time is finished around 44 seconds. That is when almost everything is below the 80 degrees Celsius. Okay, so you see that with this program, we can check if we can reduce the cooling time, if we can reduce the packing time, how to place the gate, which is the runner system that could be better for us according to the simulations, and so on. Okay, so this is basically what we've done is explained in this computer session. And then we have some exercises that it's very basic exercises that you can do it by yourself if you want. That is just to compare with another part that is pieza A that it's in the folder, in the files, and you can do exactly the same like this computer session and check the maximum pressure and the packing time that it's defined according to the solidification that I showed you here in this example. Okay, so this is what I wanted to show you. So more or less, I think that this is the end of this part and this course. I don't know if in these 10 minutes that it's missing for finishing the class, if you want to ask anything that you want, or if you see something that could be better to to add in future courses or whatever, I don't know. So feel free to say whatever you want about this last part of the presentation and of the course. But basically, this is this is like a short version of the content that I teach in the master degree here at the university. I also teach CAM system, machining systems with SolidWorks, but this is just for injection. Okay.